Hello everyone. This is group number 12, and our topic is high temperature solder alloys composition and reliability evaluation in power semiconductors. So, first of all, I would like to start with what are power semiconductors. So, power semiconductors are different from the semiconductors which we use in microprocessors and chip. The difference here is the power semiconductors are specially designed to handle high voltage and high current, and the key parameter that is necessary here is that they have to dissipate heat very efficiently as compared to that of the semiconductors used in the microprocessors and chips. So the main process which takes place in the power semiconductors is rectification, voltage conversion, inversion. They are specifically used for in the the voltage inverters and everywhere. So as we can see in this diagram, the power semiconductors are used in various products like air conditioner, automobiles, televisions. All the appliances which consumes high power are the recipient of power semiconductors. So Infineon is one of the company which is leading in the power semiconductor domain.
Mm.
They, as Professor Pradeep Dikshit sir has told us, like they are a sort of the integrated device manufacturer which design, fabricate, and do the packaging of the power semiconductors. So, how does power semiconductor differ from microprocessors? Because microprocessors and memory tasks manage computing and memorization tasks, while power semiconductors are
बोल तू बोल सकता है
optimized for efficient power transfer.
तू बोल सकता है म्यूट है
So, this is a broad classification of
हाँ
how
तो
power
4 मिनट का
semiconductors
हो
can
जाएगा ना
be
4 मिनट बोलना है मेरे को
classified into. So,
चार
they
मिनट
can
बोलना है
be classified into low voltage, low current
4 मिनट बोलना है यार
applications,
लगभग
low voltage, high current applications, high voltage, low current applications, and high voltage, high current applications. So, the low voltage, uh, low current applications are used in the our consumer electronics like flexible devices, sensors, smartwatches. So the key parameter here is they operate on the voltage below 50 volts and the current is less than 1 ampere. So the working semiconductor types, as we have CPU, GPU in microprocessors, here it is the high power MOSFETs, which is different from the MOSFET which we use in the microprocessors. There are bipolar junction transistors which convert, it is basically a sort of transistor which converts AC to DC, and a low power insulated gate bipolar transistor, which is a modified version of MOSFET and BJT. And the low voltage high current power semiconductors, the voltage range is roughly in the range of 60 volt, and they draw current close to 60 ampere to 800 amperes. So these are the applications like battery charging system, welding equipment. And the same thing is the same the semiconductors used are MOSFETs, low voltage IGBTs, and low voltage thyristors. Thyristors is one type of a device which works on it's kind of an inverter. And the high voltage low current is where the voltage range which it works is above 1000 volt, and the current is in the milliampere range. So this is particularly used in particle accelerator, medical imaging, and electron microscope. And the same thing with high frequency, high power, and high voltage is being used in these devices. And the fourth one is the high voltage, high current devices, and they operate in a voltage range about 1000 volts, and they draw currents in thousands and hundreds of ampere. So silicon carbide and other high power devices as mentioned here are being used in this. So there are applications particularly in inverters, electric arc furnaces, and other applications. So why is silicon carbide and gallium nitride preferred instead of silicon? This is because the switching frequency of gallium nitride is more than 20,000 megahertz, while that of silicon is less than 10,000 hertz. This means that the on and off state, which Professor Pradeep Dikshit had told us in the class of MOSFET, the on and off state, the speed with which the on and off takes place is very high in the place of in gallium nitride. And the thermal conductivity of gallium nitride is and silicon carbide are way better than that of silicon. Because of the higher band gap of gallium nitride and silicon carbide, they have a higher mobility and the saturation velocity, which is basically the maximum voltage which it can carry. And similarly, it has a higher breakdown voltage. As we can see in this image, there's this silicon based charger which is 65 watts. The size is very huge. Because of the switching frequency, we can miniaturize the semiconductor in a much better place. So the charger which you see here, which we typically use for 65 watt, is because gallium nitride has a better switching frequency than that of silicon. So in when if we are talking about the packaging technology, uh, like in contrast to the packing technology being used in the microchips, where flip chip and 3D packaging and hybrid bonding is preferred. In specifically in power semiconductor technology, we only need the better efficient heat transfer. So here, still wire bonding is the most preferred technology here, and the substrate used is basically silicon carbide, silicon, and sometimes sapphire. So why is silicon carbide and silicon used? Because we cannot use directly gallium nitride on gallium nitride, because the if you want to use gallium nitride directly with gallium nitride semiconductor, like it is very costly to develop a gallium nitride substrate for gallium nitride. And the thing is, silicon is not typically used as a substrate for gallium nitride because there is a lattice mismatch when we use gallium nitride on silicon. This leads to potentially leads to defects. And as we have been learned in the class that we need a ceramic based substrate here for better heat dissipation, as to avoid the coefficient of thermal mismatch. So the coefficient of thermal mismatch here is very low in this case. So in this diagram we can see, so there are high power MOSFET, silicon carbide, insulated gate by insulated transistor, thyristor, BJT, and other semiconductors. So they have been classified as per the power requirement here.
Thanks, Ravis, for this. Uh, Thanks, Ravis, for for the previous slides. I am Vikas Singh from group number 12, and I will be explaining the problem statement. In this, high temperature solder alloys play a critical role in power semiconductor packaging, particularly in die attach and substrate to base plate attachment. Even in devices that use wire bonding for interconnects, these alloys ensure reliable thermal and electrical connections under high operating temperatures. Here, um, this slide addresses the need for alternative solder alloys instead of SAC. What is SAC? Uh, tin, uh, tin, silver,
Silver.
copper
Sure.
in power semiconductors. The first one is SAC melting point is 220 degrees Celsius. Operating temperature is 150 degrees Celsius. Here, the SAC alloys melt at 220 degrees Celsius but operate up to 150 degrees Celsius, whereas power semiconductor requires solders that withstand 250 to 300 degrees Celsius without softening. So this is the problem with this with this SAC. And the second point is high temperature solder alloys must withstand 250 to 300 degrees Celsius without softening or remelting. So brittle intermetallic compounds that are IMCs. SAC forms brittle phases like Cu6SN5 and Ag3SN, which weaken join reliability. So that's the issue. And the third one is formation of brittle intermetallic compounds, IMCs, like this Cu6 SN5 and Ag3SN. In this, thermal cycling failures, that is SAC joints crack and delaminate under repeated thermal stress due to rapid crack propagation. And the fourth one is cracks propagate rapidly in SAC joints under thermal cyclic, leading to delamination. So performance demand. Power semiconductors that are used in EVs, inverters, and many more need materials with higher thermal stability and mechanical resilience. Now come to next slide, that is current technology used in power semiconductors. So what are the current technologies used? We are using that tin, as SN, SB, AgCu alloys. This slide uh, details the composition and properties of these alloys used in high temperature applications. So the composition is tin, that is used up to 25 to 52% as a base material, and antimony, that is used as 35 to 40%. So now, when we come to this, so the alloy composition, as I mentioned above, acts as base metal. Tin acts as base metal, providing ductility and forming the matrix. Antimony enhances the strength and creep resistance by forming hard intermetallic phases, that is SBSN. SB also suppresses tin whisker growth. A common failure mode is SN-rich solders. Silver, that is used up to 8 to 25%, improves electrical conductivity and refines the microstructure by forming Ag3SN, which strengthens the solid solder matrix. Copper, that is used up to 5 to 10%, increases mechanical reliability by forming CuSN bond in IMCs, which enhances interfacial bonding with copper substrate. And there are few trace elements that are aluminum, iron, and many more, that are up to 1.5%. These additives refine grain structure, reducing voids and improving resistance to the thermal fatigue. Now the second is uh, microstructure. So the here the primary phase SBSN intermetallics dominates, providing high temperature rigidity, and secondary phase finally dispersed Cu6SN5, Cu3SN, and Ag3SN particles act as reinforcement, preventing dislocation movement under stress. And the third is eutectic regions of SN-rich phases, that are SN-rich phases improve ductility, balancing the brittle IMCs. And the next point is uh, thermal properties. Solidus temperature is up to is more than and up to 280 degrees Celsius. Ensure the solder remains solid during high power operation. That is in electric arc furnaces or SiC based converters. We use this. Liquidus temperature, that is below 400 degrees Celsius, allows processing at temperatures lower than ceramic substrate degradation. Its threshold is up to 450 degrees Celsius. For example, we take an application in SiC power modulus for EVs. SN, SB, AG, Cu solders are used to bond chips to direct bonded copper uh, substrate. Their high creep resistance prevents joint deformation during prolonged high current operation. And then let's come to slide 8, existing issues and future research. Let's come to existing issues. So the challenges and research directions. Uh, let me take the first point. High processing temperatures. Melting points above 200 degree Celsius require energy. Intensive reflow processes, increasing manufacturing costs. Excessive heat can also damage temperature sensitive components like organic substrates for thin film sensors. And the second point is poor wetting ability. Lead-free SN-SB-AgCu solders exhibit inferior wettability compared to lead-based alternatives. Poor wetting leads to incomplete joint formation and creating voids or weaker bonds. Flux additives are often needed, but these reduces residues can corrode interface over time. The third point is brittle IMCs. While SBSN phases enhance strength, they reduce ductility. During thermal cyclic uh, cracks initiate at SBSN Cu6SN5 interfaces, especially in CTE mismatched assemblies, that is silicon to copper joints. Mm, Sorry. The fourth point is oxidation during soldering. So at high temperature, SN oxidizes rapidly, forming SnO2 layers that hinder solder's flow. This necessitates inert atmosphere, that is nitrogen, during soldering, adding complexity to manufacturing. And the next is thermal fatigue. In CTE mismatched systems, that is silicon chips on AIN substrate, repeated thermal cyclic induces stress. Over time, this causes crack propagation in solder joints. For example, uh, Yamada ETLL 2006 observed cracks in SN-SB-AG CU joints after just 200 cycles, and in the atmosphere is in between 40 to 105 degrees Celsius. And the next point is component compatibility. Some PCB finishes, that is ENIG OSP, react unfavorably with SB-rich solders, leading to interfacial delamination. And additionally, is toxic. SB's toxicity, though lower than lead, raises concern in certain regularity environments. And the next point is mechanical reliability. Long-term durability under vibration remains unproven. And the next point is future research. In future research, there are few points, that is noble alloys. Bismuth-based solders are being explored for their low melting points, that is up to 270 degrees Celsius, and reduce brittleness. However, Bi3Ni intermetallic forms formed during cyclic remain problematic. And the next point is nanoparticle reinforcements for enhanced strength and reliability. Uh, and the next point is advanced characterization techniques for better understanding of failure mechanism. Let's come to industrial researches. Uh, here, here there are 2 points: improved simulation models for predicting long-term reliability, and the second point is development of CTE meshed designs for better joint reliability.
Hello everyone, I'm Adarsh Prajapati and I'll be describing some of the ongoing work on this field of alloys for power semiconductors, solder alloys for power semiconductors. So one such material which can be used for this is bismuth. So about bismuth, bismuth is a brittle material with a melting point of around 270 degrees Celsius. But some of the positive qualities are that it is no low cost and it is non-toxic as well. So if we mix bismuth with other materials, then they can give us desired properties for a solder. So one such example is mixing bismuth with copper, aluminum, magnesium to form a solder. So if we have a matrix of bismuth and we mix these particles, then uh, it can give us the desired properties which are evaluated later. So here in this figure, you can see the process of fabrication of this, and you can see the microstructure also for this solder. So if we go about the reliability and performance analysis of this solder material, then some ingots were formed with these dimensions, and they underwent the EDM testing, the tensile test, and this is the graphs of stress strain that were obtained. So this is the comparison between bismuth and the solder alloy, and this is the different graphs at different temperatures. Also, I have attached the X-ray photograph of the sample before testing. So here you can see some cavities and some hollow areas also in this sample. Now, after this, we went to the thermal property analysis, and for this, the uh, alloy went under thermal cycling test, which is used to test the fatigue, the thermomechanical fatigue, and the temperature was changed from -40 to 200 degrees Celsius around 2000 times for 40 minutes. And we use three types of samples in this. The sample looks something like a chip, a substrate, and a solder material in between. So what's different in these three samples is the coefficient of thermal expansion and the layer of the solder. So the first sample has a mismatched coefficient, means chip and substrate have different coefficient 4 and 17. So this showed the most poor performance because there were cracks observed in this solder layer after 200 cycles only, and with very low temperature difference of -40 to 105 degrees Celsius. But for CT match samples, the performance was relatively better, and they sustained up to 1944 cycles. But there were some intermetallic compounds like there were some other compounds like Bi3Ni also found for this. So uh, so among these three samples, we found that sample 3 is performing this Bi3Ni, which is a brittle material. So we shouldn't rely over a solder like this. But the sample 2 has shown significantly good performance. So this can be a better material for the solder applications.